what you see here is a direct measurement of the light field. This light field is in the near infrared, and it looks like an oscilloscope image of such a light field. It almost is, in a way. And the second message from this slide is that you can control the oscillations of the carrier under the envelope with the precision of much better than 1 femtosecond, so a few tens of attoseconds. This is the temporal resolution that is achievable. What you see here are just two possible realizations of what is nearly a single cycle light pulse. And this development is chiefly due to Lefteris Goulimakis. Okay, sorry. I have to say that, yes, I agree to being recorded. The second part is high harmonic spectroscopy. Again, this is a kind of spectroscopy that is not broadly known because usually spectroscopy is very slow. This is ultra-fast spectroscopy. And to date, it has the best temporal resolution achievable down to 10 attoseconds. So 1/100th of a femtosecond. The idea is that you take a medium of quantum systems, you send your laser field on it, and what you're interested in learning is what the charges are doing. And you learn this by looking at light that these accelerated charges radiate, and then you do something totally crazy. You record all of the light that's being emitted, and the bandwidth that's being emitted is now reaching into kilo-electron volts. So it's extremely broad. And then you do something even more crazy. You measure not only the intensity, but also the spectral phase across the whole spectrum. It cannot be done across kilo-electron volts, but it can be done today across few tens of electron volts. And this is what gives you such unique temporal resolution. If you're interested, there's a paper in Nature. I think last year, Lahoti is the first author. Lefteris Goulimakis is again the chief engineer behind this, the temporal resolution that they have achieved in solids, and is 0.1 femtosecond. So you can look at dynamics of charges in atoms, in molecules, and in solids. Okay, now this are our targets. I'm going to talk a little bit about graphene at the end. Mostly I'm going to talk about gapped graphene. That's what you see is graphene in real space. You see graphene in the reciprocal space, and you see the band structure. Again, I don't know how much I should tell you about the band structure, but please feel free to stop me at any time. If I do not get to the end of my talk, that's okay, because there's all kinds of results. And even if I get only to the middle of my talk, still there is something to be learned. At least that's the hope. So these are the famous Dirac points here, and there is no gap in graphene, which is a problem. Of course, you can open the gap. There are many materials which look like graphene, but they're made of different atoms. In my case, they are blue and red, and they have different energies or ionization potentials. As a result, you open the gap. And the other thing that happens when you open the gap is that there is also a beast that shows up, which is called the Berry curvature. This is really almost a geometric magnetic field that sticks through the plane of this two-dimensional sheet, and it is responsible for two effects. If you drive electrons with an electric field across this sheet of gapped graphene in the plane of the screen, then the Berry curvature would deflect the electrons, and you would actually see this deflection in many ways, in particular in light that they would emit as they're being deflected. And this Berry curvature is also responsible for the intrinsic angular momentum of the Bloch states. And that is very important for the next slide. So now we're going to, what I'm actually going to talk about, I'm going to talk about Velitronics, petahertz Velitronics in graphene and in gapped graphene. And it started, and it is now almost exclusively, is in gapped graphene materials, for example, hexagonal boron nitride. This idea uses, this is the idea from 2007, basically it points to the fact that because of the intrinsic angular momentum associated with the Berry curvature, which is different in the two valleys, there are this K and K prime valleys. So that's the K valley, that's the K prime valley. They are completely identical as far as the band gap is concerned, but they have different Berry curvature here and here. They're depicted with different colors, blue and red. So then if you take a laser light which is circularly polarized and is tuned on resonance with the gap, then by choosing the circularity of light, you can decide which valley you're going to excite. And you can promote electrons selectively into this valley or into this valley simply by choosing the polarization of light. And this has started the field of Velitronics. Now, if this computer would want to switch the slide, I would be very grateful. But it doesn't. It's like totally frozen, of course. So I think I should stop sharing the screen and start sharing the screen again.
Shut down your microphone.
Wait a second. Oh yes, now it works. Something works. No, it works now. The slide has changed. Okay. So you do whatever you want to do. At least I have slides under control. I feel very happy about it. Okay, so once you look at the scheme, you realize, well, if you need to tune your laser field exactly on resonance with the band gap, there are two issues that arise. One is that it is system specific, so you change your material, you have to change your laser. Maybe this is not a big headache. If you're working with long pulses, but if you're working with short pulses, this is a big headache. And resonances, they seem to imply that this process is inherently slow, and we're talking about petahertz. So I want to do something within a few femtoseconds. So how fast can we make this scheme? Can we go to a single cycle regime? That's the question. And the answer is yes. You just run the simulations for the laser pulse, which is circularly polarized. The pulse is shown to you at the top. Okay, now the laser pointer doesn't work, but at least it works here. So it's shown to you at the top. There are two colors, blue and some other color. I think it's kind of dirty orange. And these are the two components of the light field along two orthogonal axes, X and Y. It is a single cycle pulse. This can be done, and you see that we have selectively excited the values we wanted, and the other values are empty. Okay, so this works. This is not really a big surprise. But now here comes something that, at least to some of our co-authors, was a surprise. Suppose now we take simply linearly polarized laser field. Then, of course, we fire this laser field. This laser pulse is here, right here. The first one, the dark yellow, it will not select a valley, of course. It will equally well populate all 6 valleys in this hexagon. But now, with a delay, we come with another pulse, which is orthogonally polarized. And the system, of course, thinks, well, it's a circularly polarized pulse as long as it preserves coherence between the valence band and the conduction band between the two pulses. And then you destructively interfere out population in K prime valley in this case, and you enhance population in K valley, which is what you see. So these are more populated than these ones. Yeah, and this you can switch very quickly within a fraction of a femtosecond. I can switch from this valley to this valley by simply delaying the second pulse, the blue pulse, by half a laser cycle. So this also works. And this allows us to design a sequence of pulses that is going to move, kind of move excitation between the valleys, and therefore think about implementing not quantum logic, the classical logic, but at extremely fast rates. So here are snapshots of what is happening in this system after a sequence of 4 pulses. First, you see the first pulse. It is linearly polarized, populates equally all valleys. Then the next pulse, the blue pulse, arrives. It's orthogonally polarized, and it's timed properly with the accuracy better than half cycle or quarter cycle. It creates populations here, and it kills populations here. Then the next pulse arrives. Everybody is equally populated. And then the fourth pulse arrives, and we have switched excitation from this valley to that valley. Okay, so we have implemented some very trivial classical logic, but it is extremely fast. So far, all of our tricks used resonant or nearly resonant light, and that, of course, requires matching a laser to a material. Again, as I explained, experimentalists working with short pulses, they don't like this idea. And so the question is, can we find a way that is non-resonant and therefore may work for our favorite ultrafast light sources? Suppose it's a titanium sapphire laser, and our favorite material, which could be hexagonal boron nitride. And here the key idea is to shape polarization of light to fit the symmetry of the lattice. And the reference is at the bottom. So this is what we have proposed. You can use circularly polarized light, and you can combine 2 frequencies, fundamental and second harmonic, and they're rotating in opposite directions. If you overlap these 2 pulses, then the Lissajous figure, which is formed by the electric field within 1 cycle of the fundamental, is a trefoil. You can see it here, yeah, hopefully. And you can probably immediately see that this symmetry is kind of similar to the symmetry of the sublattice in my gapped graphene. And of course, what I can do, I can rotate this trefoil figure, and all I need is to control the relative phase between the fundamental and the second harmonic. If I change the relative phase, this whole Lissajous figure is going to rotate. And the question that we asked ourselves is the following. It's clear that we can fit the trefoil to either the gray sublattice or the green sublattice in real space. What does it do in the reciprocal space? Does it allow us to control which valley in the reciprocal space, in momentum space, we're going to populate? And the answer, yes, it does. So here is a calculation for hexagonal boron nitride. We have chosen, in this particular calculation, the laser frequency to be very low, because, again, our experimentalists are very fond of mid-IR sources at the moment. The intensity is very high for you cold people, and it's very modest for us ultra-fast people. It doesn't burn the boron nitride. And you can see that, and the frequency, by the way, is way, way, way below the band gap. The band gap is almost 6 eV the frequency is 0.4 V. So there, it takes gazillions of photons. And we certainly can populate the valley we choose. And if we rotate the trefoil, we populate the other valley. We can certainly change the laser frequency. We can go from 0.4 V to 1 V. And the scheme works in the exact same way. And so the effect is completely general. It works for far-off resonant fields. This makes us very happy. The question is, what is the physics behind this effect? And the physics is actually, this is the only piece of quantum optics or perturbation theory, time-dependent perturbation theory that you need to know. We have, let's think in very simple terms. Let's think about the system where we only have next neighbor couplings. And these are next neighbor couplings. They are static couplings, but once the laser field is introduced, it starts to modulate these couplings. And therefore, I can introduce the change, the time-dependent change in the coupling, and I'm going to call it delta T. And so, because I have this delta T between the next neighbor, I can use second-order perturbation theory to calculate the change in the coupling to the green neighbor, the second neighbor. And this is going to be just the usual second-order perturbation theory, delta T from the site 0 to the site 1, and then delta T from the site 1 to the site 2. That's divided by the gap. It's very, very simple. And the interesting part, here is the interesting part. The interesting part is that because we have two-color field, there is a time-independent part here, which does not average to 0 after averaging over the laser cycle. And this is associated with the diagrams that involve absorption of two small photons and emission of a bigger photon. And this coupling is imaginary. Well, it's complex value, it has imaginary part. And therefore, this bicircular field realizes a Haldane type system. And we can actually make it trivial or topological, as you will see in a moment. So what is a Haldane type system? It's the system where, in addition to the next neighbor couplings, you have hoppings to the second neighbor, and these hoppings are complex valued. They have the amplitude and the phase, and the sign of the phase controls the value of the hopping control the topological state and the Chern number of the system. In particular, if you make this the T2, the coupling to the second neighbor, strong enough, you can drive the system from the trivial state to a topological state. And this is, in fact, precisely what is happening in our case when we dress our gapped graphene trivial with a bicircular field. What this topological phase transition does, near the phase transition, the gap is nearly closed or fully closed at the phase transition in a particular valley, and it opens in the other valley. And therefore, what used to be a very multi-photon transition, which required a lot of photons to go from the valence band to the conduction band, now is no longer a multi-photon transition in this cycle average picture. The gap is nearly closed, and I can choose where to close it, in which valley, in the K or in the K prime, and that's the valley I choose for the excitation. So that's basically what I'm showing on this slide. I have a hexagonal boron nitride. I have this bicircular field. If the field is weak, we have two equal gaps. And as we increase the strength of the field, we will close one of the gaps, this one, or the other one, and we can choose which one by simply orienting the trefoil. This is very, very simple, at least in theory. Experimentally, it's hard, but we hope it's going to work in the lab. Okay, how are we going to read this? We have to, of course, read this out. And there are many ways to look at the valley polarization. People do, of course, angular resolved photoelectron spectroscopy, but we want to do everything completely optically. We don't want to have any photoelectron spectroscopy. And what we do is we use the nonlinear optical response of the system. We probe it with the light, which is polarized in the horizontal direction. And because we have created the topological transition where the chair number is no longer 0, it means that the Berry curvature does not average to 0 across the whole hexagon. We have what is known as the Hall effect. And we simply look at the deflection of the electrons. And this deflection is determined by the chair number of the system. And if the electrons get deflected as they are being driven by the laser field, then of course they will radiate, and the emission they will radiate will contain polarization component in the direction orthogonal to the driving field, and this is what we look at theoretically, not experimentally. So here are the calculations, and this is now for real HBN and real molybdenum disulfide. There are two curves on each plot. There is the left plot for HBN. There is the right plot for molybdenum disulfide. The valley polarization, so this is what we can calculate by simply looking at how much we have electrons or how much charge we placed in one valley versus the other valley. It's shown in percent, and it reaches something like 60%, and this is the blue curve. And then the gray curve is the helicity of the third harmonic emitted by this material, in this case, either HBN or molybdenum disulfide, and you see that the helicity follows faithfully the valley polarization. Okay, so we have ultra-fast electronics, and we have ultra-fast readout, and this is all optical, and this is, okay, 10 petahertz, not petahertz rates, 10th of a petahertz, but that's okay. Can we move it to graphene? Of course, we're being pushed by our experimental colleagues that, you know, graphene is great. This is the preferred system. The problem with graphene is that it seemed to us that our beautiful scheme that was multi-photon and relied on opening and closing the gap selectively should fail completely and miserably in graphene because it doesn't have any gap to begin with. And this is why Velotronics never worked in graphene, at least to the best of my knowledge, and to the best of the knowledge of the referees that accepted our paper. So we still decided to try if this method with the bicircular field with the trefoil is going to work. Of course, before we had different atoms. We had blue atom here and red atom here, but what are we going to select now with the trefoil? They are all identical atoms. Well, if you look at the band structure and you look closely, they're actually not so identical. In the reciprocal space, you see these are the two valleys, and what I'm plotting here are the contour plots, these kind of reddish things. And they are not identical, they are mirror images of each other. So our trefoil, just naively, fits better into this valley than into that valley. And this is as far as the theory has gone before we run the numerical simulations, and it worked. So these are results for Velotronics in graphene, and we used the 6-micron driver. Again, this is not really a big issue. The intensities have gone much lower, and this is great. Graphene can withstand these intensities. This is experimentally confirmed. And what you see, this oscillating plot, is the valley polarization. Okay, it's no longer 60%, it's 40%. I don't care. I'm pretty happy with 40%. It is there, and it is in graphene, which was rumored to be completely hopeless for Valleytronics. Okay, I can also give you the very, very brief outline on how we are mapping out the topological phase transition. I kind of alluded to it already. And so we did also simulations in a system that does not exist, which is the Haldane system. And we simply wanted to see if we can map out the phase diagram of the trivial to topological transition in the Haldane system, looking at high harmonic generation and looking at the ellipticity of this light. That's high harmonic light. This is the phase diagram. What I am showing here on the horizontal axis is the phase of the complex second neighbor coupling. And on the vertical axis, what I'm showing is the strength of this inverse strength of the second neighbor coupling. And it shows nu equal 1. This is the chair number equal 1. This is the chair number equal -1. These are the topological states, and this is the trivial state. That's the phase diagram that we know theoretically. And this is the phase diagram read out by high harmonic generation. Looking at the ellipticity of various harmonics that you can see in different colors. These are simply different helicities of the emitted light, harmonic light relative to the helicity of the linear response. You can see the phase diagram with your own eyes. The reference is also here. Okay, so I'm done. I think I am even on time. You can read my main results, and I simply thank you for your attention.
Thank you very much for a very interesting and clear talk. And I think there is a question from Mikhail Ivanov who wanted to ask. No?
I will ask you questions later. I'm in defense of my student at this moment.
Okay, sorry. Then please, can you?
Yes, thank you very much, Misha. Very beautiful results.
Thank you.
So the question is the following. If you take now, instead of graphene or hexagonal boron nitrate, if you take transition metal dichalcogenide,
Yes.
like the
Molybdenum disulfide, for example, yes.
or disulfide, you have a very strong spin-orbit coupling. So you expect it to have already a quantum spin Hall effect.
Yes.
Now, in the moment when you put your light, this is breaking time reversal symmetry, and it wants to give you a quantum Hall effect.
Yes.
So one is Z2, the other is in the Z universality class. And by tuning the amplitude of your circularly polarized light, you should be able to stop one of the edge modes and convert it to the other direction.
I wish I could do the simulations with the spin orbit coupling.
We did already.
You did?
We have these results published.
Ah.
And now one could look at whether.
But with the laser field, or was it?
Yes, with a circularly polarized
With the
light in a
brilliant.
graphene, like a lattice with a spin orbit coupling.
Ah, brilliant.
Yeah,
Then we should talk. We absolutely should talk. Oh, this is so cool. Because we're not solid state physicists. We are hackers from atomic and molecular physics community. And so for us, of course, they're putting the spin orbit coupling and all the excitons. This is a pain, and I'm really looking forward to talking to someone who actually knows how to do it.
There's another question.
Hello. Thank you for this interesting talk. I have maybe a simple question. So normally, topological phase transitions always accompanied by a gap closing.
Yes.
But for the finite gap in your system, so is it because of you're considering finite size or because of the polarization?
No, it's because I'm making a picture before the phase transition and after the phase transition, and I simply neglected to do the picture right at the phase transition. It closes, no worries.
Okay, thanks.
Yeah. I reused this slide from some other talk where we needed to show the band structure just before and just after and make a point. They're nearly identical. And I was too lazy to make a new slide. That's all.
actually, if I can ask a question, because if for topological phases, usually there are also some topological states at the edges of the system.
Yes.
Do they play any role here in your system?
In this simulations, no. We're really looking at the bulk. And actually, this is what you asked is exactly what we're trying to do at the moment, namely look at how the edge states arise and how they behave as we do this stuff to the bulk. And this is simply something we have not done yet, but this is precisely what we're doing right now. It's a very good question. I don't know the answer, but I kind of expect to see them, of course. And I do expect fully that we should be able to move them this way or that way.
Okay, great. So if there is no more questions, we can move on to the next talk. Thank you very much once again.
Pleasure.